In this video, we'll look at integrating factors. To be more specific, we'll look at the analytical method of finding integrating factors for first-order differential equations, both linear and nonlinear. So this is an introduction, so I'll define what an integrating factor is. An integrating factor is a term. It could be a number, a constant value, or a variable, but it's just a term that's more mathematical that should be multiplied throughout the differential equation to make it exact. I put this in quotes because exact is some sort of term that we use here in differential equation to mean something that can be put together using product rule. Now, instead of just telling you more, let me just show you this with an example. Suppose we have a differential equation like xy dy over dx plus y squared equals 3x. Okay, so this is a differential equation similar to what we've looked at in prior videos before. And in the previous video, we actually discussed that such kind of differential equation can be solved by expressing the left-hand side of the equation in form of an exact differential. To represent all this. Now let's try to make a few trials and see if we can form an exact differential from this. So let's begin out and see. This is xy dy dx. So dy dx suggests that probably there was some implicit function within this that gave us this dy dx here. You could use any way you understand derivatives to try and see what this could have been originally. So let me try xy squared and see what this gives us. Using product rule, this would be, so I keep x as a constant. The derivative of y squared is 2y, but this is going to be with respect to x, plus, okay, so I keep y squared as a constant. The derivative of x with respect to x is actually 1. So there we go. So let's look at this. Is it the same as our left-hand side of the differential equation? So there we go. We have y squared. We have y squared here. We have xy. Then here we have xy. But then we have a factor of 2. And this factor of 2 does not appear in the differential equation here, and we cannot factorize it out because it will then create a half here. So that means this is not an exact differential. So let me cross this out, and you can go on making more and more trials to figure out what the exact differential could be, and I can assure you that you won't find any. So let's go ahead and try something else, perhaps a little more interesting. Let's try out x squared y squared. Let's see what this gives us. Okay, so this is going to be, if I keep x squared as a constant, then we'll have 2y. I'll just write this with respect to x plus, okay, if we keep y squared as a constant and we find the derivative of x squared with respect to x, that's going to be 2x. So there we go. Now this also does not look like this, so this is not yet the exact differential. But when you look at this, by further analysis, you realize that if you factorize out, let's see, what should we factorize out to make it look a little more like this? Let's factorize out 2x and see. So in that case, what do we have inside there? We have xy dy dx, and then we have y squared, which is exactly what we have just here on the left hand side. So what this tells us is that 2x is an integrating factor. This is very important. 2x is the integrating factor. So in order for us to solve this differential equation here, we have to multiply this whole equation by 2. Let's see that. So let's multiply the differential equation. I'll write dE, the differential equation, by the integrating factor 2x. Okay, just write that better. So let's see what that is. So we have x squared, just write the differential equation xy dy dx plus y squared equals 3x, and then I'll multiply all this equation by, okay, just multiply there by 2x. Also, all this side I multiply it by 2x, and let's see what we get. So that's going to be 2x times x squared y. That's going to be 2x squared y. Guess that's it. Okay, dy dx plus 2x times y squared. That's going to be, oops, this is a multiplication, by the way. It isn't an x. I just use that for multiplication. Okay, so plus this is going to be 2xy. That's fine. Equals, this is going to be 6x squared. Now, of course, this is mathematically still correct because we have multiplied 2x on both sides of the equation. But we already know that this left-hand side is already the exact differential that we just got here. So I'll just write that as d dx of x squared y squared equals 6x squared. That's the same as d x squared y squared equals 6x squared dx. Now, since I don't have space, let me just take integrals from here. So we'll have x squared y squared equals, what's the derivative of this? That's going to be 6 over 3x cubed. I guess that's going to be 2x cubed plus some arbitrary constant k. So there we go. That's our general solution to this differential equation. In this case, we are using an analytical method because this method works for all first order differential equations that require integrating factors. We will later look at a specific simpler method for first order linear differential equation. So let's have more examples. The first example we have here, let's call that A. So we have x dy over dx plus 2y equals exponent x squared. So let's try to analyze the left-hand side of this equation and see if we can form something very similar to this using an exact differential. So let's try out, let's see. Here we have x, then dy dx. Let's try out xy and see probably if that gives us what we are looking for. So if we keep x as a constant, we'll find the derivative of y. That's going to be dy dx. Okay, that's good. Let's continue. If we keep y constant and we find the derivative of x, it's actually 1. So this is what we have. And in as much as one of the terms looks like the term that we have in the question, we don't have a factor of 2 in this derivative. So this isn't a good choice and it won't get us anywhere. So I cross out this. Let's try out another one. Let's take d dx of, let's try out xy squared. Perhaps that would help us. Let's see what this gives us. If I keep x squared, if I keep x constant, the derivative of y squared is 2y. So this is with respect to x, so dy dx plus, if I keep y squared as a constant, I find the derivative of x. That's going to be 1, so we have y squared. Again, this does not look like our original equation in the question here, and we cannot do any factorization to get an integrating factor. So this one won't work either. So let's make another trial. Now don't worry about making trials. With experience you will be able to make fewer trials and get the right answer. So there we go, d dx of xy squared. Let's see what we have here. So if I keep x as a constant, I find the derivative of y squared. Okay, that's going to be, oops, did I just repeat the previous one? Okay, so I meant to have x squared y. Okay, so if I keep x squared as a constant, the derivative of y, that's going to be dy dx plus, okay, so my next try, I keep y as a constant, the derivative of x squared is actually 2x. So if you look at this, we actually have x as a common term. So we have x squared, yet this is just x, and then we have another x here. So we could actually factorize out the x, and then inside the brackets we have, just use this very color, x dy dx plus 2y. So that means our integrating factor is x. So I'm going to multiply this equation here, just get another color. I'm going to multiply this equation, multiply by x. So that's going to be actually x squared dy dx. So I multiply x here, that's plus 2xy. Multiply x on the right hand side, that's going to be x exponent x squared, because we already know what the left hand side is. So I'll just write that as an exact differential d dx of, we already know the whole of the left hand side. This equation here is actually an exact differential, the derivative of x squared y. This is going to be equal to x exponent x squared. This is the same as d x squared y equals x exponent x squared dx. Let's take integrals on both sides since we're running out of space. This is going to be x squared y equals, so I guess you've taken classes in integration, so you can actually find what the integral of this is. I'll not show that for this video, but this is actually done using a technique called integration by parts. So something called integration by parts. Yeah, that's a very useful technique for integrating composite functions. You should definitely check that out. So if you use that technique, you actually get the answer. I think it's something like 1/2 exponent x squared. Okay, yes, that's it. So plus an arbitrary constant, let's call that capital A. So this is the general solution to our differential equation. Okay, let's just clear up this and then just try out another example. Okay, there we go. Let's have a second example. Here we go. X exponent y sorry, dy dx plus 2 exponent y is going to be equal to x. Okay, so let's try to guess what this left hand side can be summarized into as an exact differential. So in this equation we have x, then exponent y dy dx, then here we have 2 exponent y. So if you apply some knowledge of finding derivatives of implicit functions, you actually notice that our function is going to have exponent y, because the derivative of exponent y is exponent y dy dx. That's here. Then we also have a 2 in this term here. So this 2 here suggests that we have a term that is squared. I guess that's going to be x. Let's try this out and see. It may not be the exact, but it may be somewhere close to what we are looking for. So this is going to be, let's keep x squared as a constant. The derivative of exponent y is exponent y dy dx plus, now let's keep exponent y as a constant. The derivative in that case is 2x. Okay, let's write this as exponent y. The derivative is 2x. Okay, there we go. So if you look at this equation, we could actually factorize out. I think x is a common term that can be factorized out because our original question does not contain x here. So let's pull out x. Okay, that's going to be x exponent y dy dx plus 2 exponent y. So there we go. That's going to be our differential equation. And you notice that this is what we have here. Oops. So this is what we have here. That means our integrating factor is actually x. So x is our integrating factor. And so we are going to multiply all the equation by x. So we multiply this equation by x, and this is going to be, basically that's going to be x squared exponent y dy dx plus 2x exponent y equals x squared. We already know that the whole of this is an exact differential of x squared exponent y. That's going to be equal to x squared. Okay, let's go ahead and do this. That is dx squared exponent y equals x squared dx. So if I take integrals on both sides, what we're going to have, x squared exponent y. On this side we have, what's that, x cubed over 3 plus a constant b, an arbitrary constant. So this is the general solution to our differential equation. Okay, let's take our third example. So I'll clear this. Okay, there we go. Let's have our third example. That's C. That's 2x squared y dy dx plus xy squared equals 1. Let's try to form an exact differential from this. So d dx of, let's begin by trying out this. Looks like a good idea. X squared y squared. What's this going to be? So if I keep x squared constant, the derivative of y is 2y dy dx. Let's keep y squared as a constant. The derivative of x squared is actually 2x. How good is this? Let's see, we have 2x squared y. Oh, that's the very term that is here. So that's not good because we cannot factorize out anything, especially the x, especially the 2 that we wanted to make it look like this. So yeah, this isn't good enough, so we'll cross that out. Let's take another trial. Let's try out xy squared and see. I'm only making trials on x squared, y squared, xy squared, and x squared y, because those are like very near to the original function that I'm looking at. So Okay, let's do that now. We have, if I keep x as a constant, the derivative of y squared is 2y. If I keep y squared as a constant, the derivative of x is 1. So there we go. Okay, this doesn't look so close to our original equation, but if you look carefully, I could actually say 1 over x, and then inside here I could say 2x squared y plus xy squared. So if I multiply back the integrating factor inside, I'll get this very equation. So that tells us that the integrating factor is 1 over x. So this is our integrating factor. That's our integrating factor. There we go. So let's multiply this, the original equation, by the integrating factor, 1 over x. What shall we have in that case? Okay, so we'll have 2xy plus y squared. There we go. On the right hand side, we'll have 1 over x. We already know the exact differential for this. It's actually d dx of xy squared. Okay, that's nice. Here we have 1 over x. That's d xy squared equals 1 over x dx. Let's take integrals on both sides. Oops. Okay, sorry about that. The integral of 1 over x dx. So our final solution, general solution, will be xy squared equals, the integral of 1 over x is natural log of x plus a constant, an arbitrary constant k. So there we go. That's our general solution. In some cases, the general solution is required only in terms of x. So is required as y equals something, but so you may always want to do that every time it is possible, but for functions that are too hard to explicitly express in terms of one variable, then you can leave your general solution in that form, because that looks a little bit simplified. Okay, so let's do our last example here. It's part D. So there we go. R sec squared theta plus 2 tan theta dr d theta equals 2r to the negative 1. So let's try that out. Let's take some trials of exact differentials. So d dr. Let's try to see what could be the likely exact differential for this. So look at this. This is sec squared theta, which is the derivative of, that's the derivative of tan theta. So I guess our exact differential should better have tan theta inside it, because that gives us the sec squared theta. Also we have r. I'm not sure whether that's a good idea. Okay, here we have 2. Where did this 2 come from? Probably this was r squared. So this may not be the exact differential, but at least it may be close. So let's try that out and see. If I keep r squared as a constant, and then I find the derivative of tan theta, that's going to be sec squared theta. Okay, plus, now let's have tan theta to stay constant, and then the derivative of r squared is actually 2r. Okay, how's this? Yeah, I think this is good, because if we factorize out r, then we'll have r sec squared theta plus 2 tan theta. Yes, we have it. So this r is our integrating factor. Okay, this was a little bit easier to find. although it looked complex. So that's the integrating factor. That's good. Now let's multiply this original equation by r. Let's multiply by r. So what shall we have in that case? Just get another color here. So in that case we'll have r squared sec squared theta plus 2r tan theta dr. Wait, did I miss something here? I guess that's it. This is supposed to be dr d theta. Okay, that's going to be the r d theta. Why the r d theta? Let's see what that is. Yes, the derivative of r squared is actually 2r, so we've got to have the r d theta because that's with respect to theta. Also inside here, just correct that in a moment. So let's have this tan theta. This is the r d theta, the r d theta. Okay, that's nice. Okay, so there we go. The r d theta equals, let's multiply here by r. That's going to give us 2. Okay, that's nice. So the exact differential for all this is going to be d theta of r squared tan theta equals 2. D of r squared tan theta is going to be equal to 2 d theta. If we take integrals on both sides, so the integral of d r squared tan theta equals the integral of 2 d theta. What's that going to be? R squared tan theta equals 2 theta plus a constant, an arbitrary constant k. So there we go. That's the general solution to our differential equation. Okay, so in this video we have looked at first order differential equations that can only be integrated by making them exact after multiplying with an integrating factor. So in the next video we'll look at a special form of first order equations, and those are the linear equations, first order linear equations. And those kind of equations have an easier way, a shortcut method of finding the integrating factor. So for now, let's stop here.